Hello, we're Jamal and YC. Our project is football fall detection and contact visualization. The main objective is to build a system that can recognize a possible football fall from multiple camera views and then produce visual evidence that helps a reviewer inspect the decision. Our key idea is full recognition and context explanation are related, but they're not the same task. The deep VARS model is responsible for deciding whether the action is an offense, estimating its severity, and identifying the action cause. After that decision, a separate visualization layer estimates where the visible contact occur and renders a red box in the video. In our final task outputs, we process 159 actions and render 350 clips across original and replay views. During this presentation, we'll go through the architecture, the contact localization method, the interface, the qualitative results, and the main failure cases. A useful referee assistant system must answer three different questions. First question is what happened? This is action classification task. The model distinguishes between actions such as tackling, standing tackling, high leg, holding, pushing, elbowing, challenge, and dive. The second question is it an offense and how severe it is? Well, the model predicts one of the four categories: no offense, offense with no card, offense with a yellow card, or offense with a red card. The third question we want to answer is where is the visible evidence? For actions predicted as offense, the system must estimate the likely contact location and produce an explanation video. It also attempts to classify the contact as upper body or lower body contact. Those outputs have different meanings. The model prediction is the decision layer. The red box and body part estimates are the explanation layer. Our design keeps them connected without claiming that the explanation box is itself a referee decision. Okay, so we use the SoccerNet MV4 dataset, which is designed specifically for automated football referee tasks. It contains roughly about 3,900 available actions across the training, validation, test, and challenge splits. Each action contains at least two views. Usually there is an original live action view and one or more replay or close-up views. This is important because different cameras provide different information. The wide view provides the context of a play, while a replay can reveal contact that is too small or occlude in the original view. The benchmark requires two main predictions. Offense and severity form a four-class task, while action type forms a eight-class task. Both tasks are balanced accuracy, which prevent a model from receiving a strong score simply by predicting the most common class. The dataset also includes referee-oriented properties rather than only object detection labels. Therefore, the system must understand the interaction and its meaning, not just detect the two players are moving close to each other. So this slide shows the complete processing pipeline. First, the input is a set of multi-view clips. These can include the live action, the normal replay, slow motion replays, and close-up perspectives. Second, each video is encoded by a VARS video backbone. The implementation supports like MVIT, V2S, R3D18, MC318, and S3D. Each backbone converts the frames from one camera view into a compact feature representation. Third, the features from all available views are passed to MV aggregate. This module combines the evidence across cameras and creates one shared representation of the action. Fourth, the two predictions has used the same use representation. One head predicts the action class, the other predicts offense and severity. These predictions are written to a standardized JSON format. Finally, the prediction gates, the review layer, if the action is predicted as no offense, the context visualization is skipped. If it is predicted as an offense, motion, pose, or a hybrid method estimates the likely contact region and produce the output videos and metadata. This separation is intentional. The deep model decides whether a fall occurred. The computer vision layer explains whether the visual contact appeared to occur. MV aggregate is the central multi-view algorithm in the project. Its input has 6 dimensions: batch, views, channels, temporal depths, height, and width. The same video backbone processes every view, producing one feature vector per camera. The module supports 3 polling strategy. Max polling selects the strongest value across views. Min polling treats every camera equally. Attention polling learns which view should receive more weight. Attention is especially useful because one camera may clearly show the context while another may be blocked or too far away. After aggregation, the model creates a shared feature representation. The representation feeds the A-class action head and the 4-class offense and severity head. We also implement optional classical CV feature fusion. Motion and contact features can be passed by through a small encoder and concatenated with the pulled deep video features. This allows us to test whether explicit motion cues as useful information without redesigning the entire backbone. The same shared features can also be extracted from downstream modules, including the deep body part head. This is why MV aggregate is not only a polling function, it is kind of connection point between recognition, feature fusion, and explanation. The context block is created using 3 stages: timing, pose geometry, and body part mapping. The first stage estimates when the contact occurs. We sample frames around the full window and calculate motion information, including optical flow and motion intensity. This helps prioritize frames where player interaction is the strongest. The second stage estimates where the contact occurred. Key point RCNN detects player skeletons. We compare valid body key points from different players and find the closest pair. Their midpoint becomes the candidate contact point, and the box is placed around that region. The third stage maps the contact point to a body part. The system checks which body segment is closest, such as the head, shoulder, arm, torso, hip, leg, or foot. These detail labels are then reduced to 2 evaluation categories: upper body or lower body. The implementation also supports several context sources. Motion is a classical fallback. Pose uses skeleton proximity. Deep mode uses occlusion saliency from the full model. Hybrid modes uses saliency to restrict the pose search to the region that influence the model. It makes the pipeline flexible, but it also creates several possible sources of localization error. To make the system easier to review, we developed a second version of the VARS interface. This interface can open up to 4 video views and play them in a synchronized grid. A reviewer can enlarge one camera, return to all views, change the playback speed, move through the timeline, or step frame by frame. The prediction panel also shows the ground truth when it's available, together with the top 2 model predictions for action class and offense or severity. This is useful because confidence values review whether a model is making a clear decision or is uncertain between 2 alternatives. Um, the main addition is the output video action. The interface launch the pose and the contact rendering process in a background walker. Displays progress and saves the results into an MP4. Then after the export completes, the user can open the random video directly. This turns the model from a command line classifier into a repeatable review workflow. Um,
Yeah, so for the results, here's an example that shows the final result for an action predicted as an offense with severity 3 in the action class standing tackling. The two images show different replay perspectives. The yellow skeleton indicate detected player poses, while the red box marks the estimated contact area. The text overlay also includes the model context and the predicted body part category. At this point in the recording, I'll play a short section and we can go over that. So in this clip, this is the regular clip where it kind of detects the contact a little bit before, but it was able to capture it here. So if you were a referee, you could kind of slow motion this to try to confirm that the contact occurred. And behind the scenes, this is what the detection model is doing. It has a skeleton and it will try to predict where the two skeletons cross or contact happens. So we can see here that the two skeletons kind of merge together, and that's kind of confirms that the contact occurred. We also had some other examples where it wasn't as good. So in this example, there's issues where the motion had a hard time kind of figuring out where the contact happened. So here it says that the contact happened here, but if you were a referee, it was clearly the contact's happening up here next to the head. And this is probably due to the fact that, well, it kind of gets it here later, but the initial contact does happen a lot earlier. If you're a ref, this can be kind of detrimental, so you want to make sure you have a correct call. Um, but the probable cause for this is likely due to um, the motion being too fast and a bit jittery with the frames. So adding some smoothing might help with this as a solution. The output video is is built frame by frame. So this is kind of what we saw in the examples. First, the section replay or close up is decoded, resized, and sampled. Second, pose estimation detects players and skeleton key points on each sampled frame. Third, the contact function scores candidate player pairs using proximity, motion, timing, and center of the file window and optional saliency information. If a valid contact is found, the system assigns a body part and draws the skeleton, contact point, red box, and prediction labels. It writes 2 MP4 files, a complete explanation video and a box-only video. It also saves a still image and JSON metadata describing the selected frame, contact coordinates, camera information, prediction, and body part assignment. This frame level process is the strongest practical contribution of the project, and it connects a high-level foul prediction to replayable piece of visual evidence that a human reviewer can inspect. The final processing run produced 350 rendering test clips that YC kind of talked about from 159 test actions. For body part recognition, we evaluated around 158 labeled samples. The pose and classical CV method achieved around a 46.8% coarse body part accuracy, and the body part head achieved around a 71% accuracy. This is a difference of 24%, which is quite a lot. The gap tells us that the deep model's shared representation contains useful information about the action context. It is not limited to a single nearest key point contact. The pose method, on the other hand, depends heavily on the quality of the detected skeletons and whether the visible key point pair corresponds to the true contact. There's an important distinction here because the 71% result is a body part classification accuracy. It's not a contact box intersection over the union accuracy. So this doesn't mean that every red box is correct, as we saw in the examples. We currently lack ground truth spatial context boxes for direct localization evaluation. And this is important because we need to be honest with our results. The most common pose in CV failure is over-predicting the upper body, as we saw in our failed video simulation where the contact was kind of late. Many true upper body fouls are mapped to an arm, head, or torso, and this often happens when the actual leg contact is small, covered by another player, or blurred. In those situations, the nearest visible key points may belong to the upper body, even though the meaningful contact occurs on like the ankle or foot. The deep body part head performs better because it uses the shared 400 dimensional action representation, and it can learn patterns from a full video clip, such as body motion, player orientation, and overall tactical structure. It is not a force to make, it's not forced to make this decision from one geometric point. However, the deep head is not perfect. It still confuses some upper body examples and it does not directly produce spatial contact location. The design lesson is to combine two methods. The deep head can guide, validate, or veto the pose based contact box. For example, if pose predicts upper body box, but the deep model strongly predicts underbody, the system can search another player pair, another frame, or another replay. So we ran some limitations, one being the broadcast views, the wide views. Um, this comparison here explains why the original broadcast view and the replay view should have different roles. The wide view is valuable for context, so you can see the entire pitch. It shows the positions of the players, the direction of the play, the ball, and the events leading to the challenge. This context is useful for foul recognition. However, the players occupy very few pixels. Individual legs and arms may be only a small number of pixels wide, so pose key points become noisy. Perspective compression can also make two players appear close, even when their bodies are separated at depth. Oscillation makes the problem worse because one player's legs may disappear behind another. The replay close up provides less tactical context but gives much stronger body detail. This makes it more useful for contact localization and body part estimation. Our conclusion is not that one view is always better, but the system should use a wide view for understanding the play and rank replay, or close-up views for explaining the contact. The recognition and the explanation layer can also fail independently. The VAR model can make an incorrect foul prediction because the action is ambiguous. The most useful view is missing or the class is imbalanced. Improving this part requires better training, view aggregation, and evaluation. The explanation layer can fail even when the foul prediction is correct. The pose model may select the wrong players, snap to a visible arm or head, or miss subtle lower body contact. These errors are caused by oscillation, resolution, and the fact that localization is performed after the decision. The red box is therefore a post hoc explanation. It is not learned end to end from ground truth contact boxes. A viewer may naturally treat a precise looking box as authoritative, so the interface should eventually display localization confidence or warn when the pose quality is low. The correct interpretation is that the box helps a reviewer inspect the incident. It should not be presented as independently validated referee decision. So for a future improvement plan, our next work should focus on improving evidence quality before adding more interface features. In the first step, we'd run a full dataset evaluation and report the official SoccerNet offense, severity, and action metrics alongside the body part metrics. We would also label a small contact point benchmark so localization can be measured directly. The second step would improve view selection. The system would rank replays using player scale, pose confidence, replay metadata, and visibility for both players. This third step, we would improve temporal stability. Instead of detecting pose independently for every frame, we would track players and key points over time, smooth the contact box, and fuse evidence from several views. The deep body part head could also guide or veto unreliable pose boxes. Finally, we would integrate these improvements to a VAR tool. The interface would probably side by side original and replay review uncertainty indicators and other consistent settings. The expected outcome is fewer false upper body localizations, smoother videos, and measurable benchmarks for contact evidence.